Good morning, everyone, and welcome to today's lecture. This is lecture number 12. This is lecture number 12, and we are dealing with magnetic force on loop. In the last class, we had seen what we had seen that if we have any loop, which is a closed loop, and you place a closed current carrying loop in a magnetic field, the net force on the current carrying loop is zero. Do we remember this? Yes or no? No or yes? We remember this one? A closed current carrying loop placed in a uniform magnetic field. Okay, let us let me give you a problem. This is a right angle triangle, and you have two sides L and B. The question is very simple: what is the force on the loop? This loop is placed in a magnetic field B, which is going inside. You have to tell me what is the force on the loop. I'll give you 2 minutes to do this. So, what is the answer for this question? What will be the force on this current carrying loop? Remember, this is a closed loop which is placed in a uniform magnetic field. So, the net force on the loop will be equal to zero. Do we understand this? The net force on the loop will be equal to zero. Now, if you find out, just for the sake of finding out, if you find out the force on the wire AB, the force on the wire AB will be I into L into the magnetic field, and this force is in the upward direction. I've drawn the loop wrong. Okay. The direction of current I have drawn is wrong. The direction of current should be like this. Okay, so the force on the part AB will be ILB in the upward direction. If I find the force on the part C to A, that will be I into B into B. And if you find out the direction, the force on this part will be going in this direction. Now, if you know these forces, you can simply say that the force on the part BC will be in this direction by the right hand thumb rule, and this force on the part BC will be negative of force on the part AB plus force on the part CA, because the net force is going to be 0. Do we understand this? Yes or no? Total force on this loop is going to be 0. So from there you can find out the force on the part BC. If I talk about the force on the part BC, if the question would have been just find the force on the part BC, so what do you do to find the force on the part BC? You just connect B and C by a straight line. If you just connect B and C by a straight line, you can find out the force acting on the two parts combined. So I can write force acting on the part BC magnitude wise will be the length of the line, which is L square plus B square ka root multiplied by I into B. In this way, you can find out the force on any wire, and I will give you more examples on this if the wire is in a different shape as well. So please note this down. The force on a loop, current carrying loop, closed current carrying loop placed in a uniform magnetic field is 0. Using this concept, we can solve some very difficult question very easily. I'll give you 2 minutes to note this down. The next thing that we are going to write is how we can find out force on a curved wire. And the concept is very simple. If I have to find force on a curved wire, how are we going to find the force on a curved wire? For example, I have this wire, and I will show you in a snapshot. I have this wire, curved wire, which is placed in a uniform magnetic field. And someone asks us, find the force on this wire, this pink wire. You are supposed to find out the force on this pink wire. Now, how are you going to find the force on this pink wire? It's very difficult to find out the force on a curved wire, but what you can do is you can close this loop by joining these 2 points by a straight line. So this force on the pink wire carries current in this direction, will be same as the force on this straight green wire, which is joining the 2 points. If the length of this green wire, straight wire, is L, the force on the pink wire, and if I call the force on the pink wire, this force on the pink wire, curved wire, will be same as force on the straight wire. Do we understand this? Force on the pink wire will be same as force on the straight wire, and I can write the force on the straight wire as equal to I into L cross P. So this way you can find out the force on any curved wire by joining the ends of the wire and finding the force on that ends. Do we understand this?
Yes, sir.
This is the best way to find out force on any curved wire. These are three examples that you can do. Have you noted this down?
Yes, sir.
And you can note the specific examples. If you have a semicircle like this, you have to find out the force on that semicircle that will be equal to the force on this wire. Do we understand this? Force on this would be same as force on this in the same direction. Remember, the current must be in the same direction. The force on this will be same as the force on this. Do we understand this?
Sir.
I'll give you 2 minutes to note this down. Then we write the next heading, current carrying loop as a magnetic dipole. This current carrying loop, if you look at the current carrying loop, this current carrying loop is creating a magnetic field. Yes or no? This current carrying loop is creating a magnetic field. Since this current carrying loop is creating a magnetic field, if this current carrying loop has current, which let us say is in this direction, this will create a magnetic field and it can behave like a magnet because it is creating a magnetic field. If it carries current in this direction, this thumb will give us the direction of magnetic field. This thumb will give us the direction of north pole of the magnet. So basically this current carrying loop which carries a current I and the area of this loop is A, it also behaves as a magnet and it has a magnetic dipole moment. Do you understand how it looks like a magnet? Yes or no? So every magnet, if you remember, has a magnetic dipole moment. This loop also has a magnetic dipole moment, which is a vector, and the direction of that vector is given by the right hand thumb rule. You turn your fingers in the direction of current, the direction of thumb gives the direction of north pole. That is also the direction of magnetic field created by that loop. That is also the direction of magnetic moment. Do we understand this? Yes or no? Magnetic moment of a loop. Magnetic moment of a loop. What is the formula for magnetic moment of a loop? Magnetic moment of a loop or magnetic moment of a magnet is a vector quantity, and the formula for magnetic moment of a loop is N into I into A. What is N? What is I? What is A? The magnetic moment of a loop. Magnetic moment of a loop, if I write vectorly, will be N I into A. What is N? N is the number of turns in the loop. If the loop has a single turn, N becomes equal to 1. If the loop has two turns, N becomes equal to 2. I is the current in the loop and A is the area vector of the loop. Do we understand this? Yes or no? No or yes? This is the dipole moment or magnetic dipole moment This M is the magnetic dipole moment of the loop. Do we understand this? Magnetic dipole moment of the loop. This magnetic dipole moment of the loop is same as magnetic dipole moment of a magnet. If you remember this magnet, north-south magnet, this magnet had a pole strength plus M minus M. The distance between the pole was given as Lm. The magnetic dipole moment of this magnet was like this from south to north. The magnetic dipole moment of this magnet was M into Lm. The direction of Lm was from south to north. Similar to a magnet, we have magnetic dipole moment of a loop. This dipole moment of the magnet is similar to dipole moment of a magnet is similar to dipole moment of a two charge system or electric dipole. These two charges were separated by a distance of d. The magnetic dipole moment of this magnet or the magnetic dipole moment of this dipole was directed from the negative charge to the positive charge. The magnetic dipole moment here, the magnetic dipole moment is in case of an electric dipole was directed from negative charge to the positive charge. The value of magnetic dipole moment was Q multiplied by D. Do we remember this? Yes or no? No or yes? I'll give you 2 minutes to note this down. Then let's move on. Remember, if it is a straight wire, the magnetic moment of a straight wire is 0. If you turn it, if you convert it into a square, the magnetic moment becomes I into A square, where A is the length of the side. A is the length of side, A square is the area. If you convert it into a equilateral triangle, the area of an equilateral triangle is root 3 by 4 A square. So I into root 3 by 4 A square. If you convert it into a circle, the area of a circle is pi r square. So the magnetic moment becomes pi r square into I. Remember, for a given perimeter or length, for a given length or perimeter circle has the largest area. As you can see, it is proved here for a given length. Circle has the largest area. If circle has the largest area, the magnetic moment will be maximum for a circle. Do we understand this? For a given current and a given length. For a given current and a given length, the magnetic moment for a circle will be maximum. If the current is moving clockwise, the magnetic moment will go into the paper. Do we understand this? Magnetic moment of all these are going into the paper. Do we understand this? I into the area multiplied by the number of turns. The number of turns here are 1. Therefore, the answer simply becomes I into A, or Ni into A, N is equal to 1. Do we understand this? I'll give you 2 minutes to note this down. Now, the next heading is current carrying loop in a uniform magnetic field. If you have a current carrying loop and you place it in a uniform magnetic field, what happens? Now, here I have not drawn the loop. I have shown you the loop. The loop may be like this, which is placed in a current carrying loop. A current carrying loop placed in a magnetic field. Here what I have drawn is just the magnetic dipole moment of the loop. The magnetic dipole moment of the loop is like this. So the loop may be lying like this. So the magnetic dipole moment goes like this. The angle between magnetic dipole moment and magnetic field is horizontal like this, is theta. Now we must remember a few important points about a current carrying loop placed in a uniform magnetic field. The first point is, what is the force acting on the loop? A current carrying loop placed in a uniform magnetic field. What is the force acting on the loop? Closed loop. Current carrying closed loop placed in a uniform magnetic field. The force acting on the loop would be zero. The torque acting on the loop will be n if there are n number of turns, or let me not write it in terms of n, let me write it in terms of m. That will be equal to mb sine theta, where what is theta? Theta is the angle between m and b. Vectorly, if you want to write this equation, vector equation will be m cross b. M cross b. We have seen this formula before also in the chapter on magnets. When I started this, we had seen this. Again, we are seeing this. Torque on a current carrying loop will be mb sine theta. Do we understand this? Yes or no? No or yes? If theta
Sir.
is 0, which is the case which is drawn here in this case, the theta is 0, angle is 0, then torque is 0. This condition is known as the condition of stable equilibrium. I hope you understand this T is torque. You understand this T is torque, yes or no? If theta is 180 degrees, again the torque is 0. This type of equilibrium is known as unstable equilibrium. If theta is 90, torque is maximum, and the maximum torque is m into b. At the same time, if you are talking about, this was torque, if I talk about the potential energy, if I talk about the potential energy U, the potential energy U is given by minus m into b into cos theta. Or if I write it vectorly, energy will be minus m dot b. Now this formula is valid whether it is a current carrying loop, whether it is a magnet in a magnetic field, or electric dipole in an electric field. Do we understand this? All these formulas are same. Just for electric dipole, m will be replaced by m will be replaced by electric dipole moment P, and magnetic field would be replaced by electric field. Do we understand this? Yes or no? No or yes? This is the third time I am telling you these formulae. M dot B. Now, again, in stable equilibrium, if theta is 0, when theta is 0, U is minus MB. This is U minimum, and this is the state of stable equilibrium. Do we understand this? For stable equilibrium, the energy has to be minimum. If I talk about theta as 180 degrees, if theta is equal to 180 degrees, U becomes plus MB. That is the maximum energy. Maximum energy means unstability, unstable equilibrium. Do we understand this? If theta is 90 degrees, energy is 0. I'll give you 2 minutes to note this down. Then let's move ahead. The last heading of this chapter, and the heading is force between two parallel conductors. Force between two parallel long conductors. Force between two parallel long conductors. So basically what you have are two very long wires which are separated from each other by a distance a, as you can see. Two very long wires are separated from each other by a distance c, and if you find out the force on the wires, the force between the two wires will be given by this formula, mu naught by 4 pi 2 times I1 I2 by A, or you can write it like this, mu naught I1 I2 by 2 pi into A multiplied by the length of this wire. If I find the force per unit length, F1 by L, F2 by L will be equal to force per unit length. The force per unit length, since these wires are very big, very not big, very long, it will be mu naught I1 I2 by 2 pi A. Do we understand this? Yes or no? Now you can see that if I put the distance as 1 meters, if I put the distance as 1 meters and the current in the wire as 1 ampere, then this force will come equal to 2 into 10 raised to the power minus 2. That is the definition of 1 ampere. If I put the distance between the two wires A, if I put as 1 meter, I1 and I2 I put as 1 ampere, the force will come as 2 into 10 raised to the power minus 7 Newton per meter. This is known as Ampere's law, and this actually gives us the SI definition of ampere. How much is 1 ampere? 1 ampere is the current which, when flowing in two parallel wires separated by a distance of 1 meter in vacuum, produces a force of 2 into 10 raised to the power minus 7 Newton per meter. Do we understand this? Yes or no? No, yes. Do we understand this? Yes or no? No,
Yes,
yes.
sir.
I'll give you 1 minute to note this down. And the last thing that you must remember here is the direction of force between the two wires. If the two wires carry current in the same direction, the force is going to be attractive. Same direction, current, the force is going to be attractive. If they carry current in the opposite direction, you can see the force will turn out to be repulsive. Opposite direction, if the current is there, the force is going to be attractive, and if the current is in the opposite direction, it is going to be repulsive. Same current, same direction current, attractive, opposite direction current, repulsive. Do you understand this? I'll give you
Sir.
2 minutes to note this down. Okay, then with this,
Completed, sir.
we come to the end of this chapter. In the next class, we will be starting with the next topic, which is EMI, electromagnetic induction. I hope you have understood this topic. Yes or no?
Sir.
See you in the next class with the next topic. Take care. Bye bye.